In this exam item, we've got one of these portal frames that are common in the pre-engineered steel building industry, where you end up with very narrow columns at the base, and then they get much wider at the joint between the column and the rafter beam, and then that gets real thin up to the crown, and then of course the other side is just a mirror image. That effectively becomes a 3-hinge arch situation, and so we've been asked to take a look at this situation, this model where we've got column, then rafter beam, pin supports, and the hinge in the middle. We're looking at only one specific load case of heavy snow on one side only at a half kip per foot of the 45-foot horizontal projected area. Right, so that means we don't take a half kip per foot times the incline distance. It means we take it times the 45 feet, hence that 22.5 kips. That of course acts at the centroid of that distributed load. Right, we've been given partial reactions here. This is a statically determinate problem, but to work all the way through it, that takes a little bit longer. So we've already been given partial reactions here, and what we're asked to do is to determine the remaining reactions and determine whether the horizontal reactions are correct. So let's take a look at how we might do that. Right, and so the approach there is, find the reactions. We got 1, 2, 3, 4, but 3 of them pass through a common point. So we can actually just look at the global equilibrium really easily. Sorry, here the paper's sliding all over the place. And all we got to do is set up our system. Doesn't matter whether there's a hinge there or not. We've got then the load sitting right up there. We've got reaction there, reaction there, reaction there. And so there's your AY, there's your EY. If we sum moments about point A, let's take counterclockwise positive, then we'll have 90 feet times EY, and then minus the half a kip per foot times our 45 feet. That'll be, of course, 22.5 kips times the moment arm. That is half of 45 over to A, and set it equal to 0. And we're going to find that, of course, that we've got then 0.5 times 45 times 45 divided by 2 equals 506.25 divided by 90, and that makes EY equal to 5.625 kips. Now we could sum forces in the vertical to get AY, but I prefer to not do that. I don't want to carry over error. Let's just sum moments about point E. We'll take clockwise positive this time. We'll have 90 feet times AY, and then minus, once again, 1/2 of a kips per foot times 45 feet for the load, and then its moment arm this time is 45 plus the half of 45, and set that equal to 0. We don't have to worry about any of the other reactions because they go through point E. So we got 45 plus 45 divided by 2 for a moment arm of 67.5 times 45 times 0.5 kips per foot equals 1518.75 divided by the 90, and we get AY equal to 16.875 kips. Let's sum EY plus AY just to check that, and we get 22.5 kips. That's exactly what we should have. So it looks to me like we've got the vertical reactions correct. Now, to get or do the check of the horizontal reactions, then why don't we take advantage of this hinge and come along and say, okay, we've got a vertical reaction EY here. We've got then that we just calculated as 5.625, and we have EX at, what is it, 6.32 kips. And so we've got this hinge with a shear force and well, it's not really shear, just two X and Y components, but there's your hinge. I guess that's actually point C. If we sum moments about point C, and let's take clockwise positive, then we'll have 6.32 kips, and then the heights here are, we've got 20 feet and 20 feet, so that'll be times 40 feet, and then that's got to be equilibrated by 5.625 times the 45 that we have over here. Not really drawn to scale, is it? And so let's see if that works out to be 0. Boy, I sure hope it does. 6.32 times 40 minus 5.65 times 45 equals a minus 0.325, very close to 0. There's probably a rounding error sitting right here in the 6.32 that is causing the problem. And indeed, if we divide by 40, we'd find out that about, yeah, that'd be out there. 6.328 maybe is what that number might have been. Maybe that should have been rounded to 6.33. So that's part A. And then part B is actually even easier. Determine the internal moment to be transferred at joints B and D. That's B, that's D. All we got to do is cut the columns. They have the same reaction down here, and so that column is going to look something like this. There's your 6.32. Yes, there's an axial force. At the top of the column will be a shear force also of 6.32, and then you'll have a bending moment. There's your moment B. That's just going to be equal to 6.32 times the height of 20 feet, and so 6.32 times 20 equals 126.4 kip foot. And whether it's plus or minus just depends on your particular preference of signs in the coordinate system, and so it'll be the same for both columns because the columns are identically set up in that instance.